Hello friends, I am Vijay Kumar Kamble, Assistant Professor in Electrical Engineering Department. Today we are going to see the topic equal area criteria in case of stability of the power system. So what is stability? Stability is the ability of the system to regain its original state or stable operating state under the condition or when subjected to disturbance or changes taking place in the input or output of the system. So there are two types of stabilities: steady state stability and transient stability. And equal area criteria is used to check whether the system is stable or unstable. The stability of a single machine swinging with respect to a infinite bus can be studied by the use of equal area criteria. So, figure A shows the power angle curve for an equivalent generator connected to an infinite bus. Suppose that the system is operating under the steady state condition at an power angle delta 0 when a large local load delta P within the power exporting the area is switched off. So this figure A or the first curve, both the curves are the power angle curves. They are plotted this delta versus P. So delta is the angular displacement of the rotor from the synchronously rotating reference axis in electrical degrees, and P, it is the electrical output power of the generator, or it is the mechanical input power of the generator. In stability studies, we are considering input power is always equal to output power of the generator. Then the system is lossless system, and we have a swing equation PA equal to PM minus PA. So in this first figure, let us say the system is operating at a steady state condition and the corresponding angle is delta 0. Corresponding angle is delta 0 and the corresponding input power is PI 0. Corresponding input power is PI 0. So at the steady state operating condition, PM and PE both are same, and as PM and PE both are same, PM minus PE will be the 0, that is accelerating power is 0. So at the accelerating power is 0, we are saying that the system is operating at a stable operating state or stable operating condition. Now let us say that there is a sudden increase in the mechanical input. Let us say delta P is the change in the mechanical input, and the mechanical input changes from PI0 to PI1. Now here the mechanical input changes, but electrical output doesn't changes instantaneously or at that instant. It will take some time. So at the instant when mechanical input changes from PI0 to PI1, or delta P is the increase in the mechanical input. So we will see that PM is having a higher value than the PA. So PM minus PE will be a positive value. That is, accelerating power will be positive. When accelerating power is having a positive value, the rotor will start to accelerate. The rotor will start to accelerate means it will start to move in, or it will start trace the curve in this direction, that is from position 1 to position 2, position 2 to position 3. When it going from or traveling from position 1 to position 2 and comes at position number 2, that time the electrical power becomes equal to the input power, but due to moment of inertia, the rotor never stops at this position. So it will move in the forward direction, that is, it will move from 2 to 3, and from 3 again it will start deaccelerating. So acceleration will take place from 1 to 2, 2 to 3, and deceleration will start from 2 to 3 to 2 and 2 to 1. Now why this stops at 3? So while accelerating from point 1, while it is moving from 1 to 2, the rotor is gaining some kinetic energy. Whatever the kinetic energy gained during this acceleration period is shown by this area A1 or by this dotted line, and this area is represented as area A1, or this area is also called as the accelerating area, and this area is nothing but it is the kinetic energy gained during the accelerating period. So when it comes at this point, the rotor is having some kinetic energy, and with the help of this kinetic energy, this will move in the forward direction. That is, when the rotor is moving from 2 to 3, the kinetic energy which is stored in the rotor will be lost. So here the kinetic energy will be full or will be maximum, and as the rotor start accelerating from 2 to 3, this kinetic energy will be lost in this region, and at point 3 the kinetic energy will become 0. So the rotor will stop at this position, and again it will start to decelerate in the opposite direction. So it will start decelerating from 3 to 2, 2 to 1. So whatever the kinetic energy lost during 2 to 3, that is shown by the dotted area, and that area is represented by A2. This area is also called as the decelerating area. So when rotor is accelerating, it will move from 1 to 2, 2 to 3. The corresponding angle at 1 is delta 0. The corresponding angle at point 2 is delta 1, and the corresponding angle at 3 is delta 2. Initially we are at delta 0. Initially when the system is stable, that time the corresponding angle is delta 0. Now due to increase in the mechanical input, due to change in the mechanical input delta P, it changes from delta 0 to delta 1, and at delta 1 the system will become stable. Now how to recognize or how to know that the system is stable or unstable? So we have two areas. One area is called as the A1, or this area is also called as the accelerating area, and another area is the area A2, that is the decelerating area. When accelerating area becomes equal to the decelerating area, or when area A1 becomes equal to area A2, then we will say that the system will be stable. But if there is a change in the area, that is area A1 is not equal to area A2, then we will say that the system is unstable. So to know the system whether it is stable or unstable, if the two areas are equal, then the system is called as a stable system. So this criteria is called as a equal area criteria. This criteria is called as a equal area criteria, because the stability in the system can be checked by the two areas, that is area A1, which is called as accelerating area, and the area A2, which is called as a decelerating area. And when both these areas are equal, the system will be stable, and when both these areas are unequal, the system will be unstable. So this criteria is called as a equal area criteria. Now what will be the maximum limit for the equal area criteria, or what will be the maximum limit to become the system stable? So it is given by the limiting case is 180 degree minus delta I1, or delta M equal to 180 minus delta 1. What is delta M? Delta M is the maximum allowable angle at which the system will become stable. So here also the initially angle is delta 0 due to increase in the mechanical input. Due to sudden change in the mechanical input, the mechanical input becomes greater than the electrical output, so the system will get accelerated. The system will start accelerating from point 1 to point 2. At point 2, both the powers, that is mechanical input power and electrical output power, becomes equal. So here the accelerating power should be the 0, but due to moment of inertia and the kinetic energy which is stored during this area A1, the rotor will move further in this direction. So from this point it will go on losing the kinetic energy, and at point 3 whole kinetic energy will be lost. So this area A1 and this is the area A2. If both these areas are equal, then we will say that the system will become stable. Now, beyond delta M, what will happen? There will be lesser area for A2, and this area A1 will be greater. So A1 will be greater than A2, or we will say A1 is not equal to A2. So whenever A1 is not equal to A2, the system is called as a unstable system. And when the system is unstable, it will lose the synchronism. So the maximum angle at which the system can become stable, that is the delta M. So delta M is the maximum angle so that the system will become stable. Thank you.